So now I'm going to talk about cluster validation, which is basically how a couple of measures that you can use in order to validate whether your clustering is good or not. And it's different because you can say, well, you know what, I can validate simply by looking at the cost of my optimization, right? Whatever optimization I ran. Yes, but that cost is specifically to your clustering algorithm that you used. So it would be very hard to compare that to other clusterings if you have if you're using the specific internal cost function of that clustering algorithm. So I'm going to talk about external validation, so to speak, where these validations are not coming from a specific algorithm. They can be used to compare different ones. And also, I'm gonna give an example, like a practical example of a paper that uses clustering to look at some interesting things, and hopefully give you an idea of how clustering is used in research, at least. We have a question from David. I think some people are missing since Moodle is down. They could not get a Zoom link. Oh man, that's a bummer. I did put the link in Slack, or did I not? I think I did. If I didn't, then I'm really stupid. Yeah, okay. So yeah, so I guess there was no other way in that sense. So yeah, that's a bad thing, unfortunately. So let's go to cluster validation. Each of the presented techniques has their own pros and cons, of course, and considering that, a few questions arise. How can we check if the clusters are good partition of the data set? I mean, you know, there will never be a final solution to this. These validation metrics that I'm going to present to you, they are attempts to having these independent, let's say, metrics to evaluate clustering. But there will never be a final solution to that. And how can we find good parameter settings? By comparing different results. So you can use them not only to actually compare different clustering algorithms, but you can also use them in order to choose parameters, right? So if you have to search a hyperparameter space, then you can use one of these validation metrics in order to determine whether one setting of parameters is better than the next one. This is one idea of comparing to ground truth. So yeah, so in this case, this is interesting. In this case, you can compare the results that you get from the clustering with an actual ground truth that you already have, which is called like external validation. So in this case, we're back to supervised in a sense, because even though the clustering itself is not supervised, you validate the results with external validation. So it could be good, for example, if you're testing a new clustering method, because maybe you say, well, but you know what, why would I use that if I have the labels? Then I just do a classification because it becomes a supervised problem. Yes, but maybe you have a new clustering method that you're trying to evaluate. So it's like, oh, should I use this new clustering method instead of the one that I'm already using? One way to choose that, to decide for that, is to take a data set that you have labels for, that you use to do supervised learning, and then you apply the clustering, and then you say, you know what, let's look at how the clustering results do in comparison with the actual classification problem that I have, just as a way to determine whether the clustering method itself is good or not. And then maybe later you use this clustering method with another data set that you don't have labels for. But still, by doing the external validation, you have evidence that the method itself is good. Okay, and maybe it's a similar data set, so then you can kind of like transfer, so to speak, this validation to the next one, even though you don't have labels. So one of the ways of doing this is by comparing the clusters you have with the labels that you have, right? And how would you do that? Well, for example, this Jacquard coefficient uses these definitions of SS, SD, and DS, which is basically, in a nutshell, SS is the number of, let's say, the set of pairs of points that are in the same cluster and the same class, right? So you have points in the same class, and then you apply clustering, then you have points in the same clustering, and then you take 2 points and you say, okay, are these guys that are in the same cluster, are they also in the same class? if the result is yes, if the answer is yes, you put them into this SS set of points. If two points are in the same cluster, you detect them to be in the same cluster, but actually when you look at the class, they're not in the same class, that's let's say an error, right? So you're clustering, that is not very good for your clustering. So you put them into this SD set of points. And on the other hand, if 2 points are in the same class, so you take these pair of points, they are in the same class, but then you look at them and they are not in the same cluster. So you didn't detect that, you detect them to be in different clusters, then you put them into this DS bucket, let's say. And then finally, you just compute your coefficient as being the number of points in the SS bucket divided by the sum of all the 3 buckets. So the points in the SS, the points in the SD, and the points in the DS, this will give you like a normalization term, so to speak. And then you basically find the number of correct predictions, so to speak, divided by the total number. And this will give you your Jacquard coefficient. Then that's one coefficient that will give you a measure of the total intersections between clusters and classes. Like intersection between a cluster and class is a good thing, because that means the cluster kind of detected your class, so to speak. And this would give you a validation of your clustering, again, based on external data that you have. So, you know, you can only use it if you have external labels. Purity is a different one. It's again external validation. It's again comparing to ground truth. So again, it applies to all those cases that I discussed in the previous slide, where you have the labels, but you still want to validate your clustering. So it's more like a validation step. And then you compute this purity thing, which is the sum of, well, you compute this max in regards to J. You compare because, okay, so the purity here is, the idea of purity is that you have to assign a cluster to a class. Okay, so differently than what you had in the previous measure, which we didn't really care about whether a cluster was equivalent to a class, so to speak. Because if you have, let me try to clarify this. If you know that you have 3 classes, because we're doing external validation, so we have classes. Then if you know you have 3 classes, for example, then you use k equals 3 to find 3 clusters. If you can define k. If you don't define k, then it doesn't matter. But if you do define k, then you find 3 clusters. Now the next question is, which cluster is assigned to each class, right? Because there is no specific connection between a cluster and a class. So the first thing you have to do is to find which cluster is assigned to each class. And this is more or less what you're doing here. Is for every class Pj, you have an intersection with a cluster K, right? And then you take the one that has the biggest intersection with the cluster, and then you assign that, you kind of connect them. You say, okay, the cluster K is connected to the class Pj. They're more or less the same. Let's say the cluster is representing the class. And then you take and then finally you say, okay, how many points are actually correctly predicted to be in this class by this cluster? Then you sum everything, and that's your purity. So your purity is like how many points the cluster has gotten right, because it is also in the correct class. It almost feels like supervised learning in this case, but it's not. It's almost like classification without supervision, so to speak. You could actually consider it as being that, because you asked for 3 clusters, you got 3 clusters, and then you tried to determine how much these clustering got right when compared to the actual classes. So that's what this max term here is saying, is the maximum overlap between clusters and classes. And this is an example of a result. So for example, here we have 6 classes. So P1, P2, P3, P4, P5, P6. These are the 6 classes that exist in the data, because you have this data. Then you apply clustering. So you also get, 6 clusters. So C1, C2, C3, C4, C5, C6. And then you look for the intersection between these things. So for example, C1 has an intersection of 506 points with P4, which is a class 4. So basically you say, okay, C1 is, let's say, attached to class 4 because C1 is kind of like predicting class 4. Then C2, the largest number of overlaps is with class number 3 because you have second cluster has 280 points in common with class number 3. So we kind of attach them together and say, okay, C2 represents class number 3, and so on and so forth. So each cluster kind of gets attached to one class. And then finally, you go and you take how many points the cluster got right. So the first cluster got 506 right. The second cluster got 280 right. Third cluster got 671 right, and so on and so forth. You sum all of them and then divide by n, which is the total amount of points that we have in the data set, which is not the same as this sum, of course, or else that would be 1. So, and then you could kind of say, okay, you know what? This clustering has a purity of 72%, 0.72, because we got this clustering, this as a whole got, let's say, 72% of the points right in this definition of what a right is. And some interesting things to look at here is that, for example, C4 and C6 were attached to the same class. There's no restriction about that. There's nothing we can do about that. So basically, the clusters 4 and cluster 6 were attached, so to speak, to the same class. And class 5 did not have any clustering assigned to that, which is also possible to happen. There's no way to determine that each cluster will be assigned to each class. So that happens. And you can see, for example, C4 had 162 points in common with class 2, but it also had 119 points in common with class 4. So you see that C4 is kind of ambiguous. It's not, even though we attached it to class number 2, you can't say for sure that it's for sure connected to class 2 because it also has a lot of points in common with class 4. So we draw a line there. We take just one, but actually it's very ambiguous. And C6 is also kind of ambiguous because, okay, it has 358 points in common with class 2, but it also has 212 points in common with class 4. So as you can see, C4 and C6 here, they have more or less the same pattern. They are connected to both classes 2 and 4. So maybe a new measure could maybe take that into account, but it's not the case with this one. So there's always these ambiguities when you were dealing with unsupervised learning. That's how it is. And then you get this purity point and this purity score, and then you can use this to compare different clustering, either different clustering algorithms or different settings of the same clustering algorithm, and maybe choose which one is the best. Now there's an internal validation, which is a little bit more interesting because now it's not supervised anymore. Now it's actually just the clustering itself. You don't need labels for that. You don't need anything for that. It's just really this kind of measure of quality of clustering that is completely independent of the algorithm and also completely independent of labels. And by far, the silhouette coefficient is the most common measure for clustering. So if you have to use something to determine whether your cluster is good or not, it's probably silhouette. I'm not saying it's good because I don't know. It's hard to say. How could I possibly say if it's good or not? But it's for sure the most common one. It's for sure the one that most people use. And so if you use that, also people will understand and accept, let's say, the results as being as best as we can have right now. It combines cohesion and separation. So it combines both intra-cluster distances and also inter-cluster distances together in order to arrive at a final score, okay? Which is interesting because that's what every clustering algorithm wants, right? And no matter what the algorithm does, what you want is to have good intra-cluster cohesion, let's say, or it has to be cohesive. The distances inter-clusters should be small, and there must also be good separation. So the distances between the clusters should also be good. This is for all clustering algorithms in one way or another. And this is what the silhouette coefficient measures. So for every point xi that belongs to a certain cluster, ck, you compute two things. And there's all these math here, but I'm just going to go for the intuition. The intuition is that A is the average distance from xi to all other points of the same cluster. So you take xi, which is a point from the cluster, compute the distances to all other points, take the average, and then do it again for the next one and the next one, so on and so forth, right? Then you have B, which is the average distance from xi to all points of the neighboring cluster. And again, this is the definition here with its minimum. It's the same thing that we saw with purity, for example. That's similar to what we saw with the purity, which is I want to find, so the concept of a neighboring cluster is not something that's written in stone. It's not something that is super clear. But basically we consider as being the neighboring cluster is the cluster that has the smallest distance, average distance to that point out of all the other possible clusters. So every point will have a different one, right? Because some points are, let's say, to the right, so they have a certain neighbor cluster. Some points are to the left, and they have another one. So then you have A, which is the average distance within the cluster. You have B, which is the average distance to the neighboring cluster. And then you use A and B in order to determine the silhouette coefficient, which is basically 1 minus A over B, which is if A is lesser than B, which it is most of the time, because the intra-cluster distances should be smaller on average than the neighboring cluster. Sometimes it isn't, and then you have to invert the computation here, or else it becomes crazy. Well, here anyway. So it's then you take, so A over B, which is the average, sorry, not the average, it's the proportion between the internal and the external distances, right? So A over B. And then you do 1 minus. And the reason why you do 1 minus is because you want to score. So you want something that when it's 1, it's good. Because the smaller this one thing here is, and the larger this one thing is, then this becomes very small. And then 1 minus something that's very small is 1, which is what you want, because it's a score. You want to say, if it's 1, it's good. Yeah, so, and then you invert it if for some reason A is actually larger than B, so the intra distances are larger than the external distances. Shouldn't happen, but sometimes it happens. And then you got your silhouette coefficient, and it goes between -1 and 1. I thought I had written this somewhere here. No, it goes between -1 and 1, even although it's usually larger than 0, unless your clustering is completely bogus, then it's not, but usually it's larger than 0. And this is just a representation here of a visualization, actually, of the silhouette coefficient of every point in the data set. So, you know, the cluster 0, cluster 1, cluster 2, cluster 3, and cluster 4. Every line here, you can't really see the lines because there's a lot of points, but every line here is 1 point. And then you can kind of look at the silhouette of every point here and determine whether it's good or not. There are some interesting things here. For example, there's this little tail over here which goes below 0. This is the situation where we said where the intra distances are larger than the external distances, and they are the orange points. So probably some points in somewhere over here in the middle have smaller distance to cluster 2 than they have to cluster 4. And then, so obviously they're very wrongly assigned, but it happens anyway, so you see them here. And this line over here is the average. It's this line over here is like what you would report as being the final silhouette. So if you just want one number, you take the average, and then that would be like 0.50 something. That would be your silhouette. But maybe it's also interesting to look at the visualization. So you look at the distribution of the silhouette. For example, you can see that the silhouette for cluster number 2 is in general lower than average, also for the orange one. So then you can kind of deduce that the orange and this teal colored cluster are not very, it's not that they're not very good, but since the silhouette is lower than average, then you see that there's some confusion there. While at the same time, when you look at the blue one, you can see that all of them are much larger than the average. And if you look at the visualization, then you can see that the cluster number 1 is very far away from the other clusters. So it's very clear. The separation of cluster number 1 is very, very clear. And that's reflected in the very large silhouette values. And so on and so forth. So for the green ones, you can see that some of them are larger than the average, some of them are not. And then that's because it's kind of well separated. But as you move towards the border, then of course some points will be a little bit more confusing, right? And again, as you could see here, we computed AI and BI, so that was for each point, right? Because you computed for each point, and then later you just average everything, and then you have a value. But still, the points, the values for each point are also interesting to visualize if you want to have a more interesting result, more detailed results, right? So that's what visualization is for.